Hey, Chem 100 students, it's Dr. Ricardo. Today we're going to go through the Chapter 9 notes, which is chemical reactions, chemical quantities in reactions. An old-fashioned term for this is called stoichiometry. So stoichiometry is when you can do calculations that predict the amount of product that can be made in a chemical reaction based on the initial quantities of reactants. So it's very practical stuff. If you think about baking cakes, it's calculating how many cakes you can make based on the amount of all of the different starting materials that you have. So let's say you have 1 pound of sugar, uh, 2 gallons of milk, 4 eggs, and 4 pounds of flour. How many cakes can you make based on the recipe? And then obviously for cakes, you also need a little bit of baking soda or baking powder. So let's say you also had 2 cups of baking powder. So what would be the maximum amount of cakes that you can make? The other thing that you can do with stoichiometry is if that you can work backwards. If you know that you want to make a certain amount of cakes, you can calculate how much of the original reactant materials you would have needed, which is very practical because that's the best way to do things is to not waste, right? So to make only the amount of the particular product that you need for whatever situation you're in. All right, so let's get started. So the most important thing to realize is that there are going to be two ways to express the amount of materials that we have. Okay, and those two ways that are going to be critical are going to be through the amount of moles of each of the materials that we start with, or the number of atoms or molecules that we start with. Because in both cases, you can look at the balanced chemical equation and you can relate the amount of reactants to the amount of products, or one product to another product, or one reactant to another reactant. So you can do all the necessary calculations as long as you're in one of those two units. So what are those units? Atoms or molecules, which is looking at the particles individually, or moles, which is looking at a big collection of those molecules, right? So that would be 6.02 times 10 to the 23rd molecules in one place would be 1 mole. Okay, so they both have something in common. They're both counting numbers. Just like a dozen, a mole or a molecule actually counts up the individual atoms or molecules in the chemical reaction. So we'll do a couple of examples of that. What you're not allowed to do is to take the mass of something and relate it directly to the mass of something else, or the volume of one of the starting materials and relate it to the volume of the product. Those calculations won't work. You need to first convert to either molecules or moles. Now, molecules is not going to be very practical because when we're working on the scale of that we work with as human beings, the number of molecules is enormous. So we would be dragging around something times 10 to the 23rd all day long, and it would just make our calculations a lot harder than they have to be. So by first taking the number of molecules and converting it into moles, we can work with reasonably sized numbers. Like for instance, a half a mole of water turns out to be 9 grams of water. That's a practical number to work with. Can you imagine having a conversation and talking about the number of water molecules in 9 grams? If we did that, 9 grams is half a mole, so half a mole would be half of Avogadro's number. So we'd be having to say to each other, half of 6.02 times 10 to the 23rd, which is 3.01 times 10 to the 23rd. So I'd be saying 3.01 times 10 to the 23rd reacts with 3.01 times 10 to the 23rd. There's no need to do that. We can first convert to moles because moles is on the scale that's necessary to work with in lab. Okay, so let's take a look at the notes. So the first thing is a definition of stoichiometry. So stoichiometry is the quantitative relationship among the reactants and products in a chemical reaction. Okay, second thing that we want to talk about is something called the mole ratio. So let me give you the definition of it, and then I'll show you some examples. The mole ratio is the ratio between the number of moles of any two species involved in a chemical reaction. So if you have a balanced chemical reaction like the one we do down here, so first we'll make sure that it's balanced, we can look at the ratio of the coefficients to determine how many moles of this will react with how many moles of this to produce how many moles of this. So here's our very simple reaction. Okay, this is a synthesis reaction because we take hydrogen and oxygen and make water out of it, right? So we learned that in the last chapter. If we were going to balance this, these twos would not be here yet, right? We just have hydrogen plus oxygen makes water. So to balance it, the first number that we'd probably want to handle is the hydrogen number. So I've got a 2 here. I go ahead and see, well, that's balanced. But when I look at the oxygen, I've got only a 1 here for oxygen, but I've got a 2 here. So I'm not allowed to change this one. So what do I have to do? I have to double the water. So now if I double the water, that makes the oxygens correct because it's 1 times 2 here and 2 times 1 here. Well, what does that do to the hydrogen? Hydrogen has 4 now over here because 2 times 2 is 4. So that's when I need, excuse me, that's when I need to add the second 2 here. So now this overall chemical reaction is balanced. So a couple of true statements. Obviously, 2 molecules of hydrogen react with 1 molecule of oxygen to create 2 molecules of water. Another statement I could say that's certainly true is 200 molecules of hydrogen react with 100 molecules of oxygen to make 200 molecules of water. That makes sense. Well, look what I can also say. Since moles is just a scaled up version of the number of molecules, I can say that 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. Again, relating the coefficients. The coefficients are 2 to 1 to 2. Okay, so those 2 things I'm allowed to do. Obviously, the other thing I can do is I can scale up my number of moles. This is a true statement. Right? For every 50 moles of hydrogen that react, half that amount of oxygen would react, right? So if this is 50 moles, this guy's got to be 25 moles. And how much water is it going to create? Well, 50 moles here would create 50 moles here. Why? Because it's the same coefficient in front. So 50 to 25 to 50 would be okay as well in number of moles. Okay, what isn't true? Well, what you can't say is 2 grams of hydrogen react with 1 gram of oxygen to produce 2 grams of water. That is not true. The reason that is not true is because of the masses of the different molecules are so dramatically different. Oxygen is 16 times heavier than hydrogen. So putting it is not going to be just in a simple 1 to 2 relationship. In fact, the amount of oxygen that you're going to need in grams is going to turn out to be a much bigger number than the amount of hydrogen. But we'll see that in a little bit, so let's not try to get ahead of ourselves. Okay, well, just like we did, whenever you have a statement that relates to things, this time it's coming out of the balanced equation, we can stack those 2 things up into a relationship that's equal to 1. Right? So if you remember, way back when we said 12 inches is equal to 1 foot. Let me get a piece of scrap paper here for a second, right? So the very first day of the semester, we said we can relate different things that are equivalent to each other. So 1 foot is equal to 12 inches, right? So that's called a conversion factor. Well, if those 2 things are equal to each other, anytime I take something and I divide it by itself, I get 1. So I can always stack these things up. And that's a true statement. And this, the flipped over version, is also a true statement. And what am I going to do with these ones? Well, I can always use them in conversion factors to multiply the number of inches or feet that I have in my situation to calculate the number of inches of feet that I'm interested in. Okay, so super quick one. If I have 2.3 feet and I say how many inches is that? Which of these two guys over here are we going to use? We're going to use this one over here because I want feet to cancel out. So in here, I'm going to multiply by 1. I'm always allowed to multiply by 1 in math, right? It's a nice trick. So 1 foot is equal to 12 inches. Okay, so if I go to my calculator and I take 2.3 times 12, right? So I'm just doing the calculation that's right here, 2.3 times 12, I get 27.6. So that's 27.6 inches, right? Goodbye feet. So you remember those kinds of calculations. Well, that's the same thing that we're going to do, only with our stoichiometry. So all of these statements are true. 2 moles of hydrogen are related to 1 mole of oxygen. That's the relationship between this one and this one. So in that case, I'm relating 2 reactants. Okay, let's look at this one. This one just is the flipped over version. Okay, why would I need this? I would use this one if I wanted to get into moles of oxygen from moles of hydrogen, and I'd use this one if I wanted to get into moles of hydrogen from moles of oxygen. Okay, so that's the first relationship. We just related this guy to this guy. Okay, so that would be relating 2 reactants. How much of this do I need to react with how much of this? Okay, second one, let's relate the hydrogen to the water. Well, this is a 2 to 2 relationship, which you could simplify to a 1 to 1. But we're going to leave it like this so that you can show me where you got these numbers from. Again, right from here. For every, that's the way you have to start these statements. For every 2 moles of hydrogen that you start with, you create 2 moles of water. So 2 to 2 with the hydrogen on the top and the water on the bottom, and 2 to 2 with the water on the top and the hydrogen at the bottom. Sometimes you're going to need the top one. Sometimes you're going to need the bottom one. Last relationship. Let's relate oxygen to water. For every 1 mole, see that number that's not written there? That means a big fat 1. For every 1 mole of oxygen that I start with, I create 2 moles of water. Okay, so let's stack those two up. Well, here I have the 1 mole of oxygen in the numerator and the 2 moles of water in the denominator. I'm going to use that one sometimes when I want to go from moles of water to moles of oxygen. And I'm going to use the flipped over version, the fact that I can create 2 moles of water from every 1 mole of oxygen. I'm going to use that one when I'm interested in calculating moles of water from moles of oxygen. Okay, the one that I'm interested in is going to go in the numerator. The one that I want to get rid of is going to go in the denominator. Okay, so that's actually nothing new. The only thing that's new is we're adding a new step. We're relating the amounts of materials of different substances that are in a balanced chemical reaction that has a one-way arrow that goes all the way to the right. Okay, so let's take a look at some examples. So the first set of examples fall under the heading, see if I get this straight for you guys, okay, fall under the heading of mole-mole calculations. That means we're going to be starting with moles, and we're going to be doing our calculations so that we end up with moles. I just want to get my paper organized. Oh, that was dumb. Okay. All right, so that being said, put those down here. Let's take a look at our first example. First question says, how many moles of water can be produced if 4 moles of oxygen is reacted with excess hydrogen? Okay, so let me, on this paper, just go back and write the balanced equation. So our balanced equation was 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water gas. Okay, so that's our balanced equation. So what's our question? How many moles of water can be produced if 4 moles of oxygen is reacted with excess hydrogen? So what I would do in this case is say, how much of this do I start with? Okay, so the scientists decided to start with 4 moles of hydrogen. That's my initial quantity. So going through the word problem, just write down what the initial amount is. Don't multiply this by 2 yet. You have 4 moles of hydrogen that you're starting with in your beaker. All right, nobody said the amount of this. All they did was tell you it's in excess. So excess means you've got plenty of oxygen. You're not going to run out of it, so don't worry about it. Okay, it would be like talking about a plant sitting out in the outdoor environment where there's no shortage of oxygen, and that plant can grow as fast as it can based on other things, but it's certainly not running out of oxygen because there's plenty of oxygen in the atmosphere. Okay, same thing here. This is the oxygen from the atmosphere. It's in excess. Okay, so if that's the case, then this is my driver, this 4 moles. That's how much was given to you in the question, so write that down. You need the number, you need the unit, and you need the material now, right? You need to tell us which stuff you're talking about. So we have 4 moles of hydrogen. Okay, I need to multiply it by a conversion factor. Well, my conversion factor is a relationship that comes from the balanced chemical equation. If I want to see how much water I can make, I need to relate this coefficient with this coefficient. So what do I say? For every 2 moles of hydrogen that go in, 2 moles of water pop out. Okay, so there's my relationship. This time it doesn't come from the periodic table or Avogadro's number. This time my relationship between moles of one material and moles of the other comes from the balanced chemical equation. Okay, so let's take a look at this. Let's do the numbers first, right? 2 divided by 2 cancels out, right? If you wanted to do it that way. Another way you could do it is 4 times 2 is 8. 8 divided by 2 is back to 4. So I wind up with 4.0. My unit is still moles, right? Because this moles of hydrogen canceled out, and now my new unit is moles. And I not only need to say moles, you need to tell me what substance it is. Again, all of your answers for the rest of the course is going to be the number to the correct number of significant figures. This input had 2 significant figures, so this output should have 2 significant figures. Okay. And what unit it is. You can't just write the number 4. I have to take off, right? That's not correct. You need to tell me it's in moles. And the last thing, moles of what? What substance is it? So number, unit, substance. Good. All right. So that's the answer to the first one. I'm sorry. I actually did a different question. How many moles can be produced if 4 moles of oxygen is reacted? Okay. So let me go back. Okay, so I did the different question than the one that was here. I'm sorry about that. All right, that one that I did is if we started with 4 moles of this and this was in excess. Okay, so the one over here is a slightly different question, which in this case, you have 4 moles of oxygen. Sorry about that. Okay, 4 moles of oxygen, and you want to see what would happen if you reacted it with excess hydrogen. My fault, I should have read the question more carefully. So let me write my balanced equation down quickly. 2 moles of hydrogen gas plus oxygen gas makes 2 moles of water. So we wind up just doing 2 questions instead of 1. This time, the question that's listed up here, this one is given to you, and you have 4 moles of this. And this one is in excess. So if something is in excess, don't worry about it. It's not going to change the amount of product you have. You have a huge pile of this and just a little bit of this. Okay, so if I started with 4 moles of oxygen, I need to multiply it by my conversion factor. The conversion factors in these kind of questions come from the balanced chemical equation, right? So what do I say? For every 1 mole of oxygen that reacts, that goes in the denominator because I want it to cancel. 1 mole of oxygen, it's going to cancel with this. I create 2 moles of water. So 4 times 2 is 8, divided by 1, still 8. I get 8.0 moles of water. Okay, so in the example that was originally in your notes, the one that's right up here, you get 8 moles. You get 8 moles. The one that I just did was just the flipped over version. Sorry, I didn't read the question carefully. I did it as though it was 4 moles of hydrogen. But the good news is now instead of doing 1 problem, we've done 2. Okay. All right, let's take a look at the second example. Okay, so here's the second example. I'm going to block out the bottom stuff so that you don't get confused. I'm just going to go right to there. Okay. And let's move this up a little bit. How many moles of carbon dioxide can be produced by the complete oxidation, which we called in class the complete combustion, of 2 moles of glucose according to the following reaction? Okay, so the first thing that we want to just double check is let's make sure that this reaction is balanced. Now remember, complete combustion from the previous chapter is something that you're responsible for. You need to know that complete combustion means the reaction of the food or the fuel. In this case, it's a food, it's a sugar. This particular sugar is called glucose. Well, glucose solid reacts with oxygen in the presence of heat to produce 6 moles of carbon dioxide and 6 moles of water. So in order for us to do the mathematical questions, we need to always start with a balanced chemical equation. So on the exams for Chapter 9, the equations will already be balanced. But for you guys, you just want to double check that they are, okay, that I didn't make a mistake, but I should double check them myself and make sure they're already balanced. I'm not going to ask you to balance them at the same time that I'm asking you to do this. The stoichiometry is what we're working on now. Okay, so let's check. Remember, whenever we balance these, we do C, H, and O, right? So let's check the carbons. There's 6 on the left. All the carbons from the sugar wind up in carbon dioxide, so there's 6 on the right. So that guy's balanced, so we can check him off. Okay, let's take the hydrogens. There's a 12 over here. Come over here, all the hydrogens wind up in water. So how am I going to get 12? I need 6 times 2 to give me 12. So far those 2 guys are done. It's the oxygen that's the hard one because look, oxygen is in all 4 places in this case, so that's what makes it difficult. Look at that. A lot of times our fuel or food doesn't have any oxygens in it. It's just a hydrocarbon. Be careful, this one already has 6. Okay, so let's see if this 6 makes sense. So start on the right-hand side, right? So I have 6 times 2 gives me 12 oxygens from the carbon dioxide plus 6 times 1, right? I'm doing oxygen now. 6 times 1, this 2 only goes for the hydrogen. So 6 times 1 gives me 6. So 12 and 6 gives me 18. So if I need 18 on the left, 18 on the right, I got to go back to the left and get 18. Well, I already have these 6 that I'm stuck with inside the glucose. So that's 6. So I need 12 more. So how am I going to get 12 more? When I'm stuck with sets of 2, 12 divided by 2 is going to give me 6. So 6 times 2 is 12. 6 plus 12 is 18. 18 on the left, 18 on the right. So that's balanced. Okay, so let's go to the stoichiometry question. The stoichiometry question is going to give you a hypothetical situation where a scientist or a student puts some materials together and you need to predict how much product you can make or how much reactant you would need. So let's read the question carefully. How many moles of carbon dioxide will be produced by the complete oxidation of 2 moles of glucose? Okay. So here's my balanced equation. I know I have 2 moles of glucose, so I write that down. Okay, so this guy over here is 2 moles. That's my starting material. Okay, so 2 moles go in. My question is asking about the carbon dioxide. So we need to know how many moles of this come out. So I can make a little arrow coming down, and I could put a question mark. 2 moles go in. How many moles come out? Now, nobody said anything about oxygen, right? So if they didn't say anything about it, it must be an excess, right? Excess is what we call something that we've got plenty of, we're not going to run out of. Nobody asked me about how many moles of water I could make, but they could have, and I could do that calculation very easily, okay? But I'm not going to, okay? I'm only going to do the one that I was assigned. So I'm relating this to this. Okay, 2 go in, how many come out? Now again, guys, these don't have to be whole numbers. This is just a nice easy case where it turns out to be exactly 2.0 moles. This could be 1.54321, and you could do it. Okay, so first thing we do, write down the number from the question. 2.0 moles of glucose. Write down the glucose in its chemical formula, C6H12O6. Okay, multiply it by a bracketed conversion factor. So your bracketed conversion factor is going to come directly from the balanced chemical equation. That's got nothing to do with this 2 moles that went in. So what are you saying? For every 1 mole of glucose that goes in, I get 6 moles of carbon dioxide. So this thing makes carbon dioxide like crazy. One of these goes in. Why is that going to the denominator? I want to get rid of it, right? The thing that they give you is always going to wind up in the denominator. The thing that you're interested in is going to always wind up in the numerator. Hang on one second, guys. I think I may have lost this screen. Okay, I think we're back now. I don't know if you guys lost it, but my screen went out over here. So this is 6 moles of CO2. Okay, so where'd that come from? Right here, a 1 to 6 relationship. I put the 6 in the numerator because I'm interested in carbon dioxide. This has to cancel. Moles of glucose cancel out. Do the numbers first. 2 times 6 is equal to 12, right? It's 12 moles and 12 moles of carbon dioxide gas. So that's my answer. Okay, box around it. I've got a number, a unit, and a substance. Okay, so there it is. All right, example number 3. Let me just move this up a little bit. These are all starting with moles and ending up with moles. So we call them mole-to-mole calculations. Okay. So just get a little bit further here. How's that? Because I'm way down at the bottom of the page. Good. Okay. So again, in this chapter, I'm not going to be testing your balancing ability or your ability to remember the chemical reactions. I'm going to give you the balanced chemical equation. Okay. So I'll do that right here. Okay. I'll rewrite it so you have it nice and big. Hydrogen gas plus nitrogen gas makes ammonia. Okay. And it's already balanced for you. Okay. So you're going to have to trust me on that guy is already balanced. Okay. You could check yourself, but you don't have to. How many moles of ammonia can be produced from 8 moles of hydrogen reacting with excess nitrogen? Well, if this guy's in excess, you can just write that down, right? So much nitrogen that you don't have to worry about it, which this makes sense because hydrogen is hard to get in the environment, whereas nitrogen is everywhere. So if you were at an ammonia making factory, you would just suck the nitrogen right out of the air and it's basically free, okay? You just have to clean it up. The hydrogen, though, you'd have to get from another process, right? It's not free. You'd have to buy it. Okay. How much hydrogen did you start with? You had 8 moles of this, okay? Nothing special about the 8. That's just the number that was given to you in the question. Instead of 8, they could have given you 8.1 or 7.2 or 1.7. They can give you anything you want. All right. Well, there's only one product, and that's the one that they were interested in. They want to know how much ammonia I can make. So if you guys didn't remember, NH3 is ammonia, right? It's the cousin of the ammonium ion, which you know looks like this. That's one of the polyatomic ions that you have memorized. That's the ammonium ion. Here's regular ammonia, okay? So you make ammonium ion when ammonia gets dissolved in water. That's why the name sounds the same. Okay, so what's my relationship? My relationship is for every 3 moles of hydrogen that go into the factory, 2 moles of ammonia come out. Okay, so if I start with 8 moles, and how do I know it's 8 moles? Because that's what they told me in the question, right? Right up here. I start with 8 moles of hydrogen. How much ammonia can I make? So 8 moles of hydrogen, I multiply, I make a set of brackets. What's inside the brackets? The relationship from the balanced chemical equation. Okay, so the relationship from the balanced chemical equation is for every 3 moles of hydrogen that get input, 2 moles of ammonia pop out the other side. 3 goes to 2. 3 in the denominator, 2 in the numerator. Okay. All right. Now, again, when you go to do the math on this, right, you have a bunch of different choices. You can take 8 times 2 to give you 16, then take the 16 and divide it by 3. Okay. Or you can do 2 divided by 3, right, which is 0.666, and then take 0.666 times 8. Either way, there's a lot of different ways to do this. I'm going to take 8 times 2 is 16, and then 16 divided by 3. Now remember, this guy's got 2 significant digits. These are perfect numbers, right? They're called exact numbers. They come right from the balanced chemical equation. Okay, so let's do that. So we have 8 times 2 gives you 16 divided by 3 equals 5.33. This guy had 2 significant digits, so I really should stop here at 5.3. 5.3 what? Moles of ammonia, right? Number, unit, substance. Number, unit, substance. That's the way these look. So here was the original question. All right, sorry that in my notes, actually, this guy should be up here, right? Usually the balanced chemical equation is going to come with the question, and here's the work that the student did. This guy has 1 too many significant digits on here, okay? Don't worry about it, though. That guy only had 2, so I should have only come out with 2. Okay, that takes care of page 7. We'll go on to page 8 of the notes. Right, so now we got a long, ugly one, right? So what though? The idea is the process is the same. See if I just push this back a little tiny bit. How's that? Maybe too much light? I can shut that. Is that good? Okay, so here's the whole question. Okay, we'll work it out together. Again, it's in the moles to moles section, and that means I give you something in moles and I ask you about it in moles. Okay, so the balanced chemical reaction is written across the top here. Okay, sorry I ran out of room, but you're going to trust me that it's already balanced. So let's read it. Okay, this is potassium dichromate, right? So you know potassium dichromate is a polyatomic ion. I didn't ask you to memorize. Obviously, the dichromate is in the -2 state because if I reverse crisscross, that 2 had to come up here. And this guy, we know potassium's in the +1 state. So potassium dichromate reacts with potassium iodide and sulfuric acid to create chromium sulfate, potassium sulfate, iodine, like you think of, the iodine as a disinfectant, and 7 water molecules. So big, long, complicated reaction, but it's not going to make the work any harder because our job is to individually relate anything from this side to anything from the other side, something from here with something from here. You always make pairs, pair them up. You just look at 2 things at a time. Relate these 2, or these 2, or this one and this one. Any choice. You can even relate how much iodine is made every time you make a certain amount of water. Pick any 2 and you can look at the relationship between them by their coefficients. It's all about the coefficients. What are our coefficients? 1 to 6 to 7 to 1 to 4 to 3 to 7. Those are going to be the numbers that we're going to use to relate one to another. Okay, let's look at A. Question A says calculate the number of moles of potassium dichromate that will react with 2 moles of Ki, potassium iodide. Okay, they gave you 2 moles of this. I'm going to write it up here in pencil so I can erase it later. They gave you 2 moles of this, and they're asking you how much of this reacts with it. Okay, so that's the relationship. I'm relating 2 reactants. Well, this is an easy one. We can almost do this in our head, right? For every 1 mole of this that I use, I need 6 times as many moles of this, right? So I'm going to need 1/6 of the amount over here as I do over here. Okay, so what's 1/6 of 2? Well, that's 1/3. So I'm expecting the answer to this to be 0.33 moles of potassium dichromate. But let's do it and see. So what do I always do? I write down the moles of the thing that I have. Okay, all right, this, guys, comes directly from what they asked you, 2 moles of Ki. There's the Ki. Don't put the 6 in yet. We're going to take care of the 6 in a second. Multiply it by a conversion factor. This conversion factors goes inside brackets. Okay, when I'm working and comparing moles of one thing with moles of another, I get my relationship from the balanced chemical equation. For every 6 moles of Ki that go in, only 2 moles of K2Cr2O7 pop out. Okay, not in this case, not pop out, are also needed to react with it, right? Because both of these two things are reactants. Okay, so let's do the math. 2 times 2 is 4. 4 divided by 6. 4 6 is the same thing as 2/3. This guy's going to come out to 0.66, or 0.666 would be 0.67. This guy had 2 significant digits, so this guy should have 2 significant digits. 0.67 moles of K2Cr2O7. Put a box around it. Okay, so what do you think? Make sense? All right, let's see if I got it right. Here's my A. Oops. I related these guys. There's 2 here. This guy should have a 1 here. Right? Go back and look at the balanced equation there. So this guy has a 1. This guy has a 2. Excuse me, this guy has a 6. So instead of that, I get 2 times 1 is 2. 2 6 is 0.333. Okay, sorry about that. So that's 0.333 moles of K2Cr2O7. So that's correct. Okay. So what was my mistake? My mistake, I don't know why I was walking around talking about a 2 here. There's no 2 here. There's a 1 here. So there's my relationship. It's just a 1 to 6 relationship. 2 times 1 is 2. 2 divided by 6 is 0.33. Okay, sorry about that. All right, so that takes care of the first one. Let me erase what I wrote up here. And let's go on to part B. Okay, so part B, I'll leave it in a way that we could still see the overall balanced equation. I'm going to fold this over so we don't see the stuff that I wrote on already. This way I have it nice here. Okay, so let's see what part B says. Part B says the number of moles of I2, which is iodine, that will be produced from 2 moles of potassium iodide. So again, I'm starting with 2 moles of Ki over here. So there's 2 moles of here. Okay, this time I'm just going to be a little more careful. Nobody mentioned anything about the potassium dichromate. Nobody mentioned anything about the sulfuric acid, so they must be in excess. I'm not going to run out of those. And they want to relate it to how much I2 I can make down here. So my relationship is going to be between this 6 and this 3. Okay, so what's the first thing that I need to write down? Right from the question, write down how many moles of Ki I have to start with. That's my driver. That's going to drive how much of the product I can make. Okay, again, it's a nice whole number, but it didn't have to be. I could have given you this with any kind of number I wanted. It could be a fraction. It could be 0.62, and we could still do the question. All right, go back up to the balanced equation. Let me be a little more careful this time. Here's my relationship. For every 6 potassium iodides that go in, 3 iodines come out. So this guy is 6 moles Ki go in, and 3 moles of I2 come out. Okay. This has to cancel. Moles of Ki cancels with moles of Ki. So I have 3 times 2 is 3 times 2 is 6, divided by 6 is equal to 1. So this should be equal to 1 mole, right? And that should be B of I2. So here's my second one, and we just redid it here. Okay, again, where these numbers come from? Comes from this 6 here, comes from that 6. This 3 comes from that 3. We're just relating two things, one in this case from the reactant side, one from the product side. Okay, so we're going to have to erase this, and we'll keep going. Good. Okay, here's example 5. So example 5 comes from a completely different reaction. Okay, so we can do this one step or two steps. I think I'm going to do it, I'll follow the direction here. I'll do it in two steps first, and then we'll do it in one step. So let's read the question. How many molecules of water can be produced by reacting 0.010 moles of oxygen with hydrogen? Again, I have to give you the balanced equation. Okay, so we know this balanced equation: 2H2 gas plus O2 gas reacts to make two waters. Okay, let's do them all in the gas phase. So that's the balanced equation. Okay, let me see if I can move this here. How's that? Just put a couple pieces of paper underneath. Make this a little thicker. Okay. All right, so starting with the balanced equation right there. Whoop, sorry, go over a little bit. How's that? How many molecules of water can be produced by reacting 0.01 moles of oxygen with hydrogen? Okay, so let's label the balanced chemical equation with what we have. I have 0.010 moles of oxygen. Nobody says anything about hydrogen, right? So it must be in excess. Right? The thing that's in excess, we don't worry about it because we're not going to run out of it. We can make as much water as we have oxygen in this situation. Okay. All right. So let's do it in two steps. Since we have moles, we can do the moles to moles calculation. I have 0.01 moles of oxygen. How do I relate moles of one thing to moles of the other? From the balanced chemical equation. For every 1 mole of oxygen that goes in, 2 moles of water come out right from the balanced chemical equation. Okay, 0.01 times 2 is going to give you 0.02. Okay, 2 significant digits, 2 significant digits. Remember, these guys in the front don't count. Okay, goodbye moles of oxygen, hello moles of water. So this guy's going to be in moles of water. Okay, so that's the first step. Now I have moles of water. I want to go to molecules of water. Well, we know how to do that. How do I go from moles of something to molecules? Well, the way to go from moles of something to molecules is by Avogadro's number. So 0.020 moles of water times, right, brackets for conversion factor, any 1 mole of anything, including water molecules, has 6.02 times 10 to the 23rd molecules in it. Oh, sorry. Get a better eraser. So what are we doing here? We're converting from moles of water to molecules of water. We're using our universal conversion factor. Avogadro's number works for any substance. It gets you from molecules to moles. Okay, 0.02 times 6.02 times 10 to the 23rd. So we'll do that. I'll do it on a calculator, even though this one you could probably do by hand. But let's do that. Let me see if I put this over here and you can follow along. Okay, oh, I'll put it right underneath. How's that? Let's see if I put this guy over here for a second. Yeah, I think you can see everything. Okay. All right, so 0.02. Okay, so I have to go to multiply by 6.02. On this calculator, here's my daughter's calculator, here's the EXP button, 6.02. I have to change the sign, that's down here, minus 23, hit equals. Okay, well that makes sense to me. It gets a little bit smaller because the 2 times the 6 makes it 12, but look, I go down to 10 to the minus 24th. That's because of this is the 0.1 part. So this gives me 1.2 times 10 to the negative 24th molecules. Oops, sorry guys. Of water. Okay. All right, let me show you here on the nice way that we did it. Here's number 5. So that was the first step to get to moles. And the second step up here was the one that we just did. Oh, let me go back. I should not have put the minus sign on here. So let me go back. I did this calculation wrong. Let me go back and fix that. Okay, so go back to here for a second. I don't know why when I was punching it into the calculator, I punched minus 23. I should not have. 0.02 times 6.02 E, right? This guy up here, 23. No negative sign. I don't know what I was thinking. I'm a little bit off today. Equals. And so this guy's going to become times 10 to the positive 22nd. That makes sense, right? It's got to be a lot of molecules of water. Okay. Well, that's times 10 to the positive 22nd. Okay. And that's what's on the top of this page. So 2 steps. One here, and then followed by one here. Okay, so next thing I'm going to do is I'm going to do the same calculation, only in one step. And I'm going to show you that if you're given something in molecules, the one-step way makes sense because you go directly from molecules of hydrogen to, from molecules of, let me go back for a second. Molecules of oxygen. This is oxygen. Okay, from molecules of oxygen to, from moles of oxygen, they gave you 0.01, to moles of water, right? So here's our 1 to 2 relationship, and then all in one step, I multiply by 6.02 times 10 to the 23rd. So these will become more familiar to us. So that's doing this in one step. Okay, I just have to fix this guy in my notes with some white out, right? This is important. This guy is O2. Okay. Okay, so we are going to take a break right there. The next video we're going to come back with is working with something that's much more practical, and that is what happens if I start with the mass of one of the reactants and ask you how much product can be made based on the balanced chemical equation, or if I ask you for I give you the mass of one reactant and say, what is the mass of the other reactant that is needed to react with it in order for it all to go to completion? So those are the 2 kinds of calculations. So rather than starting with moles and ending up with moles, we're going to start with mass and end up with mass. The key to this is you're still going to have to go through moles. So what you're going to do is, first step, get from grams to moles using the molar mass from the periodic table. Then when you have moles, look at the balanced chemical equation to get the coefficients, because the coefficients relate the moles of one material to the moles of another material. Then the last step is go back to grams. So we're going to go from grams to moles. Then from moles of one thing to moles of another, and then back to grams. So we're going to use the periodic table in the beginning and the periodic table at the end, and the balanced chemical equation in between. This is the most important calculations of the semester, these mass to mass questions over here. So here they're called moles to mass. So this is giving you moles and asking you for mass. But this second one here really are the ones that count. This going from the mass of one material to the mass of another material. Because we don't have a tool in the laboratory. Oh, hold on one second.